You could follow our Doorless and Starknet Twitter accounts through these QR codes. After the event, we'll keep delivering good news from time to time through online. So please follow us. 행사에 대한 소개를 시작하기 전에 한 가지 안내 말씀드리겠습니다. QR코드가 테이블 위에 입장하실 때 확인하셨듯이 세워져 있는데요. 본 QR코드는 두어랩스와 스타크넷의 트위터 계정으로 연결되는 링크입니다. 그래서 행사가 끝난 후에도 종종 좋은 소식들로 여러분들께 다가갈 예정이니 많은 팔로우를 부탁드리겠습니다. I'm very excited to see Starware team and projects of Starknet in South Korea. As far as I know, it is the very first time that Starkware is officially having an offline meetup in South Korea. 오늘의 이벤트는 스타크웨어 팀과 스타크넷 프로젝트들로 이루어진 이벤트로 한국의 첫 공식 오프라인 미덕을 개최하게 되었는데요. 오늘의 이 특별한 이벤트가 정말 기대가 되는 것 같습니다. In this meetup, you'll be able to get knowledge of Starknet, and we also have a workshop ready for the Cairo, which is the development language for the Starknet. 이번 행사에서는 스타크넷에 관한 강연과 더불어 스타크넷의 개발 언어인 카이로에 대한 워크숍이 예정되어 있습니다. We have fantastic speakers joining this meetup online and offline, such as Gigi from Topology and Ellie from Starware. 또한 이번 행사에서 온라인과 오프라인으로 좋은 강연을 전달해 주실 토폴로지의 Gigi와 스타크웨어의 엘리 등 환상적인 스피커분들이 자리해 주셨습니다. So, let's jump into Starknet. Please welcome Starknet. Yes.
Hey everybody, test. Is this on? Hello.
Maybe you can use this.
Hey everybody, I am Ben. I am a developer advocate at Starkware. Thanks for coming out. Great to see you guys. Annyeonghaseyo. Sorry for the terrible pronunciation. So yeah, today we're going to be talking about Stark Volatility Rollups, the ultimate scaling technology. Just to get a feel for where you guys are at, how many of you guys are software engineers or developers? Cool. And how many have messed with Starknet or Cairo? Awesome. Cool. Well, we will go over the platform and the ecosystem with you guys. So just to set the table, kind of how things operate today, why do we need L1s? Why do we need L2s? Why does any of this exist? If you think about the landscape today, and for major applications, we really what we do is we trust a centralized party. So the example that I like to use is a bank UI. So if I'm logging into a bank UI and I want to see my account details, let's say I log in and it says I have $5. Well, really what I've done is I've delegated my accountability to a centralized entity, that centralized entity being the bank. And if you peel it back on a software engineering level, what does delegating accountability really mean? It means that I logged into a browser, into a web application that contacts an API on the back end, that contacts a database that's run and operated by a centralized entity. So I have some valuable piece of information, this $5 that I have, that's valuable to me as the user, but I'm basically saying, okay, this centralized entity, this bank, has to have a good operational security, good software engineers, competent people from their tech stack, all from top to bottom. And I basically say, you guys handle it. That's not necessarily great. I don't know if you guys have had major data breaches, but I think my information is out there on the dark web for sure from this exact issue. So I have this piece of information, this $5 that belongs to me, that's important to me. Let's go over kind of limit and bounds thinking about what's the best way to secure this piece of information and what's the worst. The easiest way, so I know some of you said that you're software engineers, the easiest way that you might be thinking is a flat file. So I'm just going to write this piece of information, $5 to a flat file on a disk. Well, that is not necessarily the most optimal because if it's just on my computer, on my on my phone and I lose my phone, I break my phone, well, that valuable piece of information, that $5 is gone. So we have this one level up, which is a database. So this is the way that a lot of the world works today: Postgres, MySQL, Oracle. These major institutions are still using databases. There's certain ways that you can organize your database. You can have a master slave or some type of redundancy. But really, if this database breaks, my $5, that valuable piece of information it's gone. So, as tech stacks have evolved, we have seen that this problem is obviously important because these solutions come about. And what's come about recently and what's kind of cutting edge is distributed systems. So these distributed systems, you might think about Cassandra, Silent, there's a whole host of different distributed systems, but what do? They replicate this valuable piece of information, this $5. They replicate it in multiple different data centers. So that is better, right? Because if I have a power outage, if someone goes into one data center, knocks down the server stack, with my $5, I have it replicated in multiple different data centers. But this red line here, what have we lost? Well, we've lost inclusive accountability. We've lost the ability for me as the user to verify that I have $5. I'm still delegating my accountability to these centralized parties to set up this distributed system. And those distributed systems are also whitelisted with known entities, known nodes. So we've come up with this thing, the blockchain, and now we don't have to have delegation of accountability. We can have inclusive accountability. I can go not trust but verify that I do in fact have $5 to my name. And that is the advent of blockchains, and that is kind of the pinnacle of where we are now, which is the evolution of user data security. But there's always a catch. Why is it slow? So I don't know if you guys have used blockchain. I don't know if you've used Bitcoin, but if you have, you might have noticed, it's kind of painful. It takes some time for transactions to propagate. It takes some time for money to transfer. So why? Why is it slow compared to banks? We have systems that do this really, really fast. We have credit cards that you can do in a transaction at a point of sale. Bitcoin was launched in 2008. Ethereum was launched in 2015. Why do they suck? Well, it's because of trade-offs. There's trade-offs in any software system, but especially so in blockchain. When you're dealing with a peer-to-peer ledger, you have to make strong decisions that last a long time. So even though we got the evolution of data security, we get the de-evolution of system efficiency. So when we're talking about what we got with don't trust but verify in the blockchain, well, what do I really mean when I say that? It means rehashing from the very Genesis block to today, every transaction that has been propagated and come to consensus on Bitcoin. So, we're spinning CPU cycles just to verify that I do in fact have $5 to my name. And then once we go past that line down, it's a similar thing, right? So distributed systems now have this extra layer of a leader election. So there's leader election amongst trusted nodes of distributed systems. Gossip protocol, network latency. You're introducing all these things to make sure that your valuable piece of information, is $15, is replicated in multiple spots. And then so on and so forth until you get to a flat file on your disk, which is just going to be the CPU to read and write to the disk. So as you evolve in data security, you devolve in system efficiency. So what do we at Starkware want to do, and why did we come up with Starknet? We love using these protocols, we love using these chains, but we want it to be fast and we want it to be inclusive. So what are our design goals? We want Starknet to be secure, we want it to be inclusively accountable. I want to not trust but verify that all of this information is in fact correct. We want it to be decentralized, we want it to be scalable, and we want it to be expressive. For expressive here, what we mean is Bitcoin has a limited subset of scripting that you can do to write applications on top of Bitcoin, but something like Ethereum has a complete programming language which you can express, a lot more on top of the blockchain with. So we want to mimic that expressiveness on Starknet. Okay, so this is kind of a rehashing of what we've gone through. So blockchains do have the inclusive accountability, but they sacrifice privacy and scalability. But we don't trust, we verify. So there's gotta be a better way. How to scale with inclusive accountability. So there's a couple different attempts at doing what we want to do. So we're going to go into ours, but you might have seen some of these other ones. So they're trusting a big computer. No, this is the wrong slide, sorry. Cool. So what do we want to do to increase the throughput of the network? Because that's really what we're talking about when we're talking about speed, is increasing the throughput of the network. So you can increase the block size, increase the block limit in the gas, and basically increase the scale to artificially augment the throughput of the network. Some networks have tried this. I don't know if you guys might have messed with Binance Smart Chain. They're one instance of this. It's worth a shot. And what it really means is that it takes larger nodes on the back end to make sure that each transaction and each execution is going through accurately. So this will limit decentralization and make it so fewer entities can actually verify the chain. Some other protocols have come around called fraud-proof rollups. You might have heard of Optimism and Arbitrum. This is an attempt at scalability through game theory. So basically they have a small window where they let someone come through and contest a state transition. If no one has contested a state transition in that window, they assume it's correct. So from a user point of view, if you're withdrawing and depositing to this layer 2 on top of Ethereum layer 1, you're going to have a wait time. And so from a UX perspective, it's not necessarily the best experience. But it does work. So our method. So instead of having this transaction compression on layer 2 that is secured by a fraud-proof mechanism and a withdrawal period in which a subset of people can put a fraud-proof in and say, we think that a state transition was done inaccurately, and then the state can roll back to the previous state of L2. There's a thing called a start proof, a validity proof. So what is a validity proof? Validity proof is a proof that the execution at layer 2 was done accurately. We do this through ZK Starks. The ZK Stark protocol, one of the founders of the initial Stark paper, Elie Ben Sasson, is actually going to be here later today. He's giving a speech right now at Biddle Asia. But it's a relatively new cryptographic system, and Stark stands for Scalable, Transparent Arguments of Knowledge. Scalable being the operative word here, because that's what we're trying to do as an L2 on top of Ethereum. So in this protocol, we have a big computer that generates the proof, which is currently run by Starkware, that generates the proof of valid execution of layer 2 to Ethereum layer 1. So we've compressed this transaction data, this transaction history at layer 2, and we write the proof, we write the state and the ZK proof to layer 1, Ethereum. So a little more about ZK proof. ZK is it's become somewhat of a buzzword. So zero knowledge proofs are this new cryptographic primitive, which you've probably heard about. That's why we decided to call ours a validity rollup. It kind of doesn't play on the buzzword, but still gets the sense of what it is. It's a proof of valid execution at layer 2 to the Ethereum L1. But let's talk about ZK proofs a little bit so you have some context. A ZK proof is also known as a zero-knowledge proof system. So a zero-knowledge proof system involves two entities, a prover and a verifier. You need both to have the zero-knowledge proof system. The prover is proving a statement to the verifier. And what is the statement? So in our language, a statement is a statement of computational integrity. That is, we are taking the initial state of the system, and we know the program that changes that state, and the number of steps that it took to change that state to its final state, S1. So we are proving a statement of computational integrity from layer 2 to layer 1 with STARKs, scalable, transparent arguments of knowledge. We'll have some time for questions at the end if you guys have questions, just FYI. Okay, so we have this system, this zero-knowledge proof system with a prover and a verifier. In our case, the statement is valid execution of Cairo code. So Cairo code is the programming language that you write Starknet smart contracts in. It's a programming language that Starkware has developed, and we hope that all of you try it. It looks like some of you guys have already written some smart contracts in Cairo. If you do come from a more Solidity background, a more traditional Web3 background, we have a transpiler. So you can transpile your Solidity code to Cairo code, and then you can prove that that Cairo code executed successfully on Starknet. So privacy, zero knowledge, again, is that buzzword we talked about, and a lot of what you hear zero knowledge used for is for privacy. In Starknet's world, we actually are not using it for privacy. So on Starknet, all of your call data is all public. There is no private information. And the reason that kind of gets misconstrued is because the prover, let me go, actually, okay. So zero knowledge proof systems have a prover and a verifier. The reason it's zero knowledge is because the prover has information that the verifier doesn't, and the verifier is still successfully convinced of the prover's execution. So what that means in other zero knowledge systems is that the prover can prove something without the verifier knowing it. You can have things like identity systems where out of this entire room, I can prove that a certain attribute about one of you exists in this room without actually saying the metadata about each one of the users. And the verifier will still be convinced of it. That setup is something that is not the reason why Starknet itself provides scalability. I'll go into it here. So the reason that it provides scalability is because the verifier does not need to know all of the transaction data at layer 2 and still be convinced of the proper execution of that. Now there's one more step, which is that we write the state proofs from layer 2 to layer 1. This is what's called the data availability problem, which is if Starknet at layer 2 went down and we didn't have some data available for each transaction, we can't rebuild the state to what it is today. So we have the prover and the verifier here. The real breakthrough here is the S in Stark, which is scalable, and that is that the prover, the verifier can verify a proof in exponentially less time than the raw execution of the layer 2 data. So the prover is verifying proper execution. In a system like Ethereum or Bitcoin, the way that we know that execution happened accurately is we just rerun the execution. And that's why it's really, really, really slow. And everyone reruns the execution. So every node in Ethereum reruns every block until it can get the state of today. And then as it gets a new block, it executes that state on top of it until it gets a new state. So in our system, you do not need to know the entire state that is being executed on L2 and still know that that state was executed correctly. And you can do it in a fraction of the time it takes to naively re-execute the code. So this is the big scalability win right here, is the asymmetry between how long it takes the prover to prove and how long it takes the verifier to verify. The other cool thing here is that the verifier can actually, it runs in exponentially less time and exponentially less computational resources. So for our verifier in the L2, L1 Starknet, the verifier is written in Solidity and lives on Ethereum. And that's what makes us a Ethereum-based roller. But this being this asymmetry between how fast it can verify and how little computational resources it has, you can imagine a verifier on a phone. You can imagine a verifier in a WASM module in your browser. A verifier can now live really wherever you have some sort of CPU. Cool, so this is highlighting the state transition that we talked about. So we still have this naive re-execution of everything on Ethereum L1. And for our purposes, we do want that. If you think back to the evolution of data security, we do want somewhere to have this kind of burdensome, large state transition. And that's what we want our state to live on. So we can always recompute the state of Starknet L2. Here's some exponentially small verifier running times and near linear prover running times. So near linear proving running times is compared to the actual execution of the layer 2 state. Yep. So now instead of don't trust verify, it's verify the start proof, don't trust. So in this way, you don't need to trust, even though we Starkware are running the sequencer and the prover, you actually are not delegating any trust to us. You know for a fact that the Cairo code was executed properly. One more point on this. So compare this to the trust assumptions of the fraud-proof roll-up systems. In that, you're trusting that some committee of fraud provers out there didn't catch a bad state transition. In this model, a bad state transition cannot occur from L2 to L1. Okay, so all of that is interesting, but what can we do? What can we build? What can we come up with? One of the things that this model gives us is this ability to do compute-heavy things on layer 2 that are actually infeasible to do on L1. So Ethereum security is delegated, but code execution and data storage are not. Starknet execution of code is trustlessly delegated to specialized actors, and storage is not. So what this means is code execution becomes much cheaper. You're going to hear from some teams today that really utilize this for what it's worth. I mean, you can really do things at L2 that you cannot even fathom or would be too expensive on L1. Like, here's a couple. So, gaming. You're going to hear from some gaming teams today. Gaming and the gaming UX on L1 is, it's infeasible to run some games on L1. Giza, so you can do on-chain artificial intelligence. This is a really cool example. This is Conway's Game of Life. So you can do permutation-based cellular automata on-chain. Everything I'm saying is on-chain. Isaac, so more gaming and on-chain information from, you'll hear from Guilty Gyoza later today. And on-chain, almost like a Stack Overflow on-chain. The community has kind of come out and built around these cool concepts and built some crazy stuff. Okay, so let's revisit the evolution of data security. We go from this flat file on your computer, which basically, if I drop my computer, it's gone. Similar thing with a database. Once we get to distributed systems, we get this feeling of redundancy. Blockchain, we get all the redundancy. Sometimes we call blockchains distributed systems, but they're really re-executed systems. Everyone with a full node has re-executed the state from Genesis to today. And then we have Starknet, which is this version of all you need to do is trust the proof. You still get inclusive accountability, and you get it via math, via polynomials, via this wild mathematical protocol that we've helped build. Okay, and let's revisit the design goals. So we set out to build a secure system. We inherit our security from Ethereum L1. We can always rebuild the state from Ethereum L1 since we write the state from L2 to L1. We get inclusive accountability for the reasons that we talked about. Decentralized, so decentralized means a lot of things. One thing we get is we inherit some decentralization from Ethereum L1, but a more concrete version of it is decentralized sequencers. So right now, we are the only ones that run a sequencer, but in the near future, what we're going to have is a P2P, a peer-to-peer layer, where anyone can run a sequencer. The reason that you want this is for transaction. Oh man, I'm blanking on the word. It just says if you submit a transaction right now and we're the only ones running the sequencer, censorship thing. If you submit a transaction and we're the only ones running the API, we could, and we don't, we could censor that transaction. Now we can't have an invalid execution of your transaction because of what we talked about with Cairo and L2 execution of Starks. But as the user, I want to minimize my trust as much as possible. So we plan on decentralizing and decentralizing soon. If you'd like to join the conversation around this, we're still speccing everything out. Join us on our community forum called Shamans, which I have the link for in just a little bit. Scalable. So we get scalable. Scalable is the first S in Starknet. And expressive. So Cairo code is Turing complete, which means that you can simulate any Turing machine, which means you can implement arbitrary code. You can do things like on-chain AI, anything you can really come up with. So we think we have expressivity. The ecosystem is really flourishing. So all of the crypto world has these cool maps of all of the protocols. But basically, every day, I can't keep up with it. Every day, a new protocol comes up, a new team pops up, a new application pops up, DeFi, NFTs, you name it. If you can think about it, you can build it. So join us, first of all. You'll see some Cairo code today. It's really not too bad to learn. I'm going to go over just a couple community tweets that I think are really interesting that kind of get my gears turning, and I hope they get your gears turning. I know a couple of you said you were software engineers from Web 2. So imagine if every public API in the world could talk with every other API in the world without going through middleware. This is the outcome when you put all your logic and state on chain. And we're building this reality at Loot Realms. This is one of the cool builders on Starknet. But yeah, if that doesn't kind of get your gears turning, what if every API could talk to every other API? And this is kind of what you get with this compute-heavy layer 2. We are iterating fast, and this actually is another community effort from Class Lambda. So the community members are rewriting some of the Cairo VM in Rust. So the Rust Cairo VM is 141 times faster than the CPython version, 25 times faster than when being run with PyPy. So community members are coming in and they're iterating on our code, and they're just optimizing everything. So every day Starkware and Starknet gets better. Every day Cairo gets better. It's a really fun ecosystem to play with. So here's some links. Like I said, this is the Shamans, this is community.starknet.io. So if you are technically minded and you want to kind of jump in on any of these conversations, stop by community.starknet.io. If you're just getting started and you want to look at some Cairo code, you want to play around with it, Starknet EDU has a bunch of tutorials. Starklings is an interactive and dynamic teaching tool, so it'll run tests as you build, as you code. Definitely check out Starklings. Awesome Starknet has a whole plethora of resources and libraries that the community uses. And then docs, definitely recommend checking out the docs for a more technical deep dive. Questions? So I'm going to open it up now. Does anyone have any questions on Starknet, CK proofs, validity proofs?
Could you go back to the slide where you're talking about way
That one?
yeah, no, so you said like the number of steps. Do you define the steps, or is that the steps that are just native to like the
Yeah, that's a good question. So, number of steps here, I'm going to give you an answer just in Cairo. So Cairo, the programming language, as you write out your smart contract logic, each operation that you write is going to involve a certain amount of steps. So what do we mean when we say steps? Cairo, C-A-I-R-O, stands for CPU air. For now, don't worry about the air, but just think about a CPU. So one clock cycle of a CPU can kind of be thought about as one step. So, yep.
So like in a scripting language, would that just be like an operation for one?
Yeah. So if you think about like, let's say you wanted to verify a signature. That is going to have a certain amount of computational steps it needs to take to verify that signature. Does that make sense? Okay. And if you want to like dig deeper down the stack, it's that you can think about Cairo like a CPU, and you can think about one tick of a CPU as one step.
But like TK proofs in the general sense, how would the step? How would you define the steps?
Okay. Yeah. So this is going to dig a little bit deep down the stack. So think about this initial state. Instead of it being the initial state of a Cairo program, think about it being the first few numbers of the Fibonacci sequence. Do you know the Fibonacci sequence? Okay. The program that changes the state is going to be the Fibonacci sequence. So you can think about it like the Fibonacci sequence is a set of rules that this set of numbers needs to take. Number of steps, you can end the Fibonacci sequence anyway. This is going to be the number of steps in which you end it at that state. So let's say that we took the Fibonacci sequence 1,000 numbers. In the ZK, in the start version of this, that number of steps is 1,000. And then the last state is that state of the Fibonacci sequence that we ended at. And that builds the statement of computational integrity.
So like just another follow-up, but you did mention like the validation of nodes, so like IBD. So in terms of IBD, what would be I guess like what would be the steps in IBD?
You said IBD?
Initial like log out, so like just syncing up to the latest states.
I think we're talking at two different layers of the stack. This is more analogous to the. Are you saying in Bitcoin or in?
I mean, just any chain in general.
Okay, so this is more talking about this would be analogous to the EVM part of it, not the blocks. So the execution of it, not the like downloaded blocks and re-execute to a certain state today. Does that make sense? So I guess a different answer would be when let's say that I download a block of Starknet now, and then we execute another block in 5 seconds. The number of steps that's going to be there for that block is going to be the number of steps that each transaction took in its Cairo execution. And we're kind of going a little out of scope for this talk because it's a little technical. But what you do is, same thing as Ethereum. You're calling a function on a smart contract, and that function has a certain amount of code in it that it runs when you execute it in a transaction. And then the number of steps is the amount of computational steps it took for that Cairo code to execute. So how many steps in a block? It's that plus every single steps for each transaction in the block.
So like each transaction and the comment or any function that resolves time exactly.
Correct. We can catch up later if you have some more questions. Yeah.
You use Fibonacci sequence as an example. And Fibonacci sequence, we know that is, even though we have like 1,000 steps, we can essentially define by one single polynomial over 1,000. So that means we need to prove one polynomial. So what happens if it's not Fibonacci sequence, it's something else, whereby there is no really nice pattern? Do we have like multiple polynomials and we need to somehow combine those polynomials to create a proof?
Okay, so if I understood correctly, if this program is defined and not followed, the program won't verify. So if you're saying that like there's something in this program that doesn't change the state uniformly.
Yeah, because the Fibonacci sequence is it changes kind of like in the same way. One single polynomial changes over 1,000 steps. So let's say we have a couple of operations, for example, like in a transaction, we have like send transfer, and then we have some other transactions in a function call. And I'm pretty sure that the way the state changes or the operation execution is very different. It's not as beautiful, easy to describe as a Fibonacci sequence. So then in such a way, what I can think of is that we need a couple of polynomials to describe the trace. So does it make sense? I mean, yes. The right way to do it, use a couple of polynomials?
Yeah, I understand. So this is, if you think about the stack of Starknet, this sits below Cairo. So this would be if you were trying to do a raw Stark, and you were trying to prove a raw Stark. So what Cairo is it's a generalized set of polynomial constraints, so that you can write any arbitrary logic. So once you're writing your Cairo code, you're proving the execution of the Cairo VM. And the Cairo VM is a set of constraints that do follow this sequence.
Okay, so allow me to ask like something even deeper, if you may allow. Mm-hmm. So that means Cairo VM essentially interpolates to create a polynomial like in the very deep level. Is that what it's doing?
Correct.
Thank you. Thanks,
Correct.
guys.
Yep.
You mentioned decentralization expresses a lot of features, but to my understanding, one of the major weaknesses of ZK rollups, as opposed to optimistic rollups like Arbitrum, is composability, specifically Ethereum composability. So I would just like to ask, because I've seen a lot of sites, a lot of articles. I'm not a tech-heavy background, but will Starknet be composable, and will it be as composable as other optimistic rollups? Any plans to make it more composable?
Yeah, that's a super good question. Starknet itself is composable with other Starknet programs, right? So we write a smart contract in Cairo, and that smart contract can mean anything. So let's say it's a DeFi protocol. On Starknet, if someone else writes another DeFi protocol, now those two can be composable together. And that's the beauty of Starknet. We do have other options like StarkX. You might have heard of StarkX. DYDX is on StarkX. Immutable is on StarkX. So those are application-specific rollups that use our technology. Those are not composable with each other. Those are just application-specific instances. So that's the reason why Starknet exists is to found that composability that you're talking about on Starknet. Now, if you're talking about cross rollup composability, that's a much bigger question. I think that's something that the Ethereum community is going to have to grapple with. Once things like dank sharding, proto-dank sharding come out, and state transitions become somewhat cheap, you're probably going to see some sort of standardization for the way that cross rollups can communicate with each other.
Thank you so much.
Yeah.
You invented the Cairo language for Starknet, and I heard that GK Sync 2.1 and yet Polygon Hasmet 2.0 are announcing the develop GK event comfortable GK event for testnet, and you guys have a plan to invent event comfortable language, or is there any obstacle to move this plan for Starknet?
Yeah. There's no formal plan for it yet. I'm going to touch on fractal scaling for just a sec. So, if you think about what we talked about today, the reason why a ZK, a validity rollup works is because we can have a prover that proves Starknet state and a verifier on Ethereum layer 1 that verifies the proofs. So what is a layer 3? A layer 3 is that verifier moved one layer up. So a verifier written in Cairo running on Starknet, verifying proofs from layer 3. So currently the EVM, or the VM on Starknet is the Cairo VM. But what you can do is you can write a ZK EVM at layer 3 that proves its valid execution to Starknet on layer 2. So one of the co-founders of Cairo language actually just sent out a tweet saying he has a code base with a proof of concept of it. There's nothing formal, but he has a proof of concept for a ZK EVM that would be at a layer 3, proving its execution to layer 2. Yeah. Any other questions? Or are we running out of time? Okay. Just grab me over there. Thanks, guys.
So how was the introduction to the Starknet? From now, one of the leading companies in Starknet ecosystem, Topology, will tell us why make games on Starknet. Please welcome Gigi from Topology.
I can. I'll just wait like this. Regulation here.
Hello everyone, I am Gyozi Gyoza. You can call me Gyozi or Gyoza, go by me. I'm a co-founder of Topology, and at Topology we're building games directly on the blockchain. We think that's the next generation of video games. Right, so I think the first question we need to answer is why make games on the blockchain at all, right? We play a bunch of video games and blockchain is a slow, expensive machine. Why do we want to make games on the blockchain? I think that there are a couple principles that we have conviction in. We think blockchain is a wonderful place for composable creations, and for all DeFi users and creators who know what composability means. It's a wonderful place for interoperable platforms, right? So things that work in platform 1 can also work in platform 2. It's not a walled garden, the meta and so on. It's an engine for collaboration and for coordination. And the advent of DAOs, although they're kind of rudimentary, I think that's along the direction of a future where massive amount of people and participants collaborate and build things together and coordinate. Right? So blockchain is a wonderful place for this. And accomplishing all these with the guarantee of immutability. Right? So if you write a program and you go on a blockchain, no one can change it, right? Unless the chain builds or something. So. But then why Starknet, right? The topic today is why build games on Starknet. So simple example maybe, I think it's important to explain what Stark is. So what does Stark, the moon map of Stark enable? And please explain like why. Okay, so the Fibonacci sequence. Imagine the 10 millionth term of the Fibonacci sequence. Right? It's an insanely huge number, right? In fact, the number is roughly like 1.13 times 10 to the power of 2 million, right? So it's a super long number. And if I tell you, okay, this insanely long number is the right answer, and you don't trust me, how do you verify that's the right answer? And this is the gist of the problem, right? I do a bunch of things, I tell you the result, and you don't trust me, so how do you verify? So Fibonacci sequence is basically just additions, right? So 1 plus 1, 2, 3, 5, 8, and you do this for 10 million times, you get a large number at the end. It takes 10 million steps, obviously, to compute, right? 10 million additions. So how do you verify it? Basically, what Stark enables is it enables polyglot verification. So you're doing 10 million steps to compute, but it takes roughly 49 steps to verify. 49 is basically log 10 million squares. So that gives you 49. Right? So it's insanely amount of scalability, right? I can do a bunch of computation, but the verification complexity is only polyglot. That's wonderful. And also it achieves completeness. So completeness basically means if I do not lie, then 100% you will verify to make sure it's right. So it's like 100% passability if the answer is correct. Now soundness means that if I lie, then you will catch it. That's basically what soundness means. And it has the probability around like 2 to the minus 80, right? So that's a tiny probability that if I lie, I still get to pass verification, which is kind of negligible. So that's why the Stark method is black magic. All right, so given this, I think that I think that a wonderful mental model that I have, which is kind of oversimplifying everything, is that I tend to think of Ethereum as like a hard drive, right? So DDR4. And I tend to think of Starknet or these CK rollups with their exotic CPUs like SRAM. Right? So we've been building applications with hard drive, right? It's pretty masochistic, right? We're just shooting ourselves in the foot while doing these things on slow machines. Now we have SRAM, we have cache, we have all these wonderful compute resources. So we should be moving to layer 2 and build more stuff instead of being masochistic and stay on layer 1, if that makes sense. Right. This another mental model I have is that I tend to think of the ecosystem as this multi-layered system. And so starting from the bottom, you have this hardware acceleration. That's what people talk about. ASICs or FPGAs or coolers. That's acceleration via hardware. On top of that, you have the operating system. So Starknet is essentially an operating system, right? It controls who writes to what, when that's allowed, and the sequence of transactions and so on. That's the operating system kind of job. On top of that, you have the ZK stack, the black magic stuff, right? So you have proof generation and verification. On top of that, you have arithmetization. That basically means transforming a computer programs into something that can be verified. So that's arithmetization. Programming language basically means Cairo and its associated compiler that allows you to write stuff that can be verified. And on top is the exciting stuff. It's the application set, right? So you use Cairo and these programming languages to write low-level libraries, and then you build infrastructure on top, and finally you build applications and front ends on the very top. The reason why we want to start Starknet is because Starkware take care of the low-level infrastructure, so then we can focus on the high-level application. It takes care of basically Starkware invented Stark. Right? They're the cryptographers in Israel that are the inventors of all the mathematical theories here. And so it's a wonderful foundation to be built, to build application on top. Right, so just to repeat, they are the inventor of Stark. They have a wonderful developer-focused culture, and I think Ben didn't mention the tokenomics that they're releasing. I think in their tokenomics there's a developer incentive. Right, so imagine a blockchain where fees accrue to smart contracts that are generating most fees. It's like if I make a low-level smart contract library where a bunch of other applications use and call my contract, then I get to receive fees as incentive from the blockchain, underlying blockchain. That basically encourages people to build more libraries that can be reused by applications. And if there's one library that's more expensive than the other library, while providing the same utility, then applications will migrate to the other utility with lower fees, right? So it's actually an incentive to sort of incubate a public good system. Yeah, and I think the last one is there's just a wonderful library of non-skeuomorphic ideas. And by non-skeuomorphism, I think that as we are making video games on the blockchain, there's a lot of wisdom in the game industry that we need to think carefully, because blockchain is a very different kind of place to build. And so a lot of these game mechanics and wisdom in the game industry doesn't really apply to the blockchain space. This mental model that I have is, I think video games we have now is like game 1.0. It's kind of like web 1.0, right? And web 1.0 is classified as something that very few people write to, most people just read, right? That's web 1.0, right? And web 2.0 is, we kind of all hate web 2, but web 2 is actually a magic, where people get to contribute content directly and contents are interlinking and all interconnected, right? I think that game still is at game 1.0. We haven't progressed to game 2.0 yet. One evidence would be, this is the statistic in the US, I think 2 years ago. The number of game industry employees versus the number of US gamers is roughly 1 to 1,000. Right? So most people play video games. When you think of gamers as a persona, there are people that consume logic programmed by the developers. They don't contribute logic. Right? And I can make a couple examples with games. These are the popular video games. So like Fortnite, right? If you build this fortress, you're essentially using the logic developed by Epic Games to instantly deploy a huge castle with all the bouncy stuff. That's Guilty Gear. So when you are using a specials, all the computer logic and the parameters that define where the hitbox is, the velocity of the special, how many frames do you need to start up versus active versus recovery from the special. All those are provided by the game developer. You're just pushing some combo keys and triggering that logic, right? This is Ghost Recon, and that is Witcher 3. All these are examples that game developers put a bunch of creativity into these logic, and we are just consuming them by pressing keys and looking at the results. That makes sense. So we think that as we are building Game 2.0, we are going to be transitioning into an era where more people are actively creating things and programming things in these next generation of video games. There's more involvement of long-term memory versus the fast muscle towards short-term memory thing, which all esports games basically encourage people to be, excelling at fast thinking, muscle memory, and so on. That's not really inclusive. A bunch of people are not that fast reactive. Right? But when we transition to a different era where most people can take the time to invent things and push things into the core game system and expanding the games together, that's a different story. So I think we're progressing to Game 2.0 and can be understood as this borderless evolutions of core games. So we are not just consuming the game logic anymore. We are participating in the evolution of the underlying core systems. Right? So you're expanding the physics, you're expanding the AI, and so on. One thing that's very important is composability. So composability is something that's actually quite simple to understand. Right? It's like if you think about writing a research paper and you have this huge topic that you don't know how to break it down, if you can't break things down, you can't tackle it. Right? So you have to, when you have a big problem, you have to think about, can I break it down into small steps and sub-problems and divide and conquer and all that stuff. That's basically composability. Right? So with composability, we can coordinate and build bigger and bigger systems. I'm just going to make a couple examples. So this is Naraka Blade Point. This is the color scheme. This is the interface where you get to edit the face of, customize the face of your characters, right? So you can move your different parts of your body and your face differently. You can dye your hair differently, customizing your avatar in the games. This can be understood as like game 1.5 maybe, like you're customizing stuff in the game, right? But you are still using the editors provided by the games. You cannot touch the underlying game code directly. This is the game customizer in Ghost Recon. Again, you are using some editor provided by the games, but you cannot touch the underlying code. This is Roblox, right? So we talk about what UGC and Roblox is a prime example. They provided this Roblox editor for people to create custom virtual worlds and little games. Still, they give you the editor. They expose you with the editor for you to change things, but they don't give you the underlying access. DocForce. So I think crypto native people would know DocForce is like the strongest pioneer of on-chain games built on layer 1 sidechain. And their mechanics is essentially DocForce. So you essentially send energy to other planets to take over and you conquer the universe. And what's special about DocForce is they have a plugin system. Right? So I can write computer code to automate a bunch of things for me. So I'm essentially running a bot network. I can create bots, I can deploy bots, I can create bots and put on a marketplace so other people can purchase and use my bots and so on. All these bots are automating actions so that people are playing at a higher playing field than what the core game system provides. And all these plugins are created by players. They're not officially provided by the developer. So we are also making games. We're making Isaac at the moment. Isaac is the color is horrible. Isaac is a game about three-body problem. So three-body problem is essentially, imagine a universe where there are three suns, right? Our universe has one sun, and so the Earth revolves around the sun in a safe and a nice way. If you have a solar system with three suns, everything is kind of chaotic, right? And the planet can go very close to the sun, it's super hot. It can go very far away from the sun, it's super cold, and it can crash into the sun and everyone dies. So that's a three sun system, a tri-solar system. Isaac is a game about this. Documentation and contracts all open source, and we are currently in closed alpha. So this is color is horrible. This is a screenshot for the actual game client. So you have three suns, and you have a planet that travels at a trajectory. Every player lives on the same planet. And so every player either win or die together. It's like a massive co-op PvE. There's no PvP incentive. And the way to avoid civilization destruction is players work together to drive their planets here and there. So imagine you're driving Earth like a car. So you're dodging the sun, and eventually you can escape the solar system. And the way they would do that is they're essentially playing the Factorial game. Factorial is like this factory resource management game on the planet. So this also is a screenshot of the game front end. So people are building these different buildings, and they're generating power, they're harvesting resources, they're transforming resources, and eventually they will build something called the nuclear engine. And when you imagine you install a nuclear rocket on the ground and you launch it, you're essentially kicking the planet in reverse, right? Instead of escaping the planet, if you deploy the rocket on the ground and launch it, you're essentially providing a reverse momentum to the underlying planet. So this is the mechanism through which players drive their planets around like a car. What's special about this Isaac, I think, is that we're the first one that ever runs physics simulation on the blockchain. So this is the very familiar gravitational law, right? The inverse law. The further away you are from me, the less gravitational pull you experience from me. That's Newton's law. And we are simulating this law with the standard numerical method, the fourth order Runge-Kutta method. And we're carrying out this computation in a small contract on Starknet. And the reason why we do physics on the blockchain is because imagine you live in a world where the underlying laws of the universe is not guaranteed to be immutable. And some single party can just mutate the laws of the universe. That would be kind of insane, right? But that's actually what all video games are. Game companies can change things arbitrarily when they think they make more money for them, for example. So that was the physics, and this is the on-chain puzzle that we put out last week as like a gating mechanism for accepting closed open alpha players. So we essentially put a puzzle in Starknet, and we say there are 50 puzzles, and when you solve one puzzle, you get a ticket to participate in our alpha. And the puzzle's in a chain, so there's no way to cheat, right? It's like when you want to play Isaac, if you haven't already solved a puzzle, then the blockchain will just refer your transaction. You get to play the game. So this is the way we kind of filter through the invitees to our alpha. Last thing we want to talk about Isaac is we think governance is very important. DAO is just at its very beginning, still in 2022. We like this idea of infinite game. Infinite game is this idea that you're playing the game not in order to win, you're playing the game in order to play more. Right? It's kind of like if your goal is to retire, then you just earn and retire, and it's just like you just go from 1 to 0. You don't work anymore, you just go retire. So like working for retirement is like a finite game, but working for building more stuff so you can build more, that's an infinite game. And we think it's important to advocate the concept of infinite game. So CarStyle is a governance structure that advocates for infinite games. And what CarStyle is that in order to have governance right, you have to play the game. So the governance right of CarStyle is not earned by, you can't buy the DAO token. The DAO token is earned strictly by playing in the game, and you sell out the game. So players will play the game. If they win the game, the result will be communicated to the DAO, and the DAO will issue voices. And voices can be mapped to votes later. So you can do like plural voting, mapping, and all sorts of exotic voting methods. And the purpose of this is we want the games to be governed not by people who have capital power, but by people that have played the game well and really understand the game. That we think is the sort of the core stakeholder of the game. Finally, these are two Starknet services that we are using to build Isaac. So Yagi is the ticker. So all video game has this ticker, right? It's just like a clock service ticking the game frame by frame. Yagi is the ticker. And Abibara is the system that indexes Starknet and organizes everything in a nice database so the front end can just talk to the database instead of having to talk to the blockchain. That just improves performance drastically. And finally, we're showing this very early tech demo. So we're making an on-chain fighting game. And so this is an internal tech demo. You have a female character with a katana, and it's like doing forward dash, backward dash, and some attack animation. What's on the blockchain is the physics. Right? So the character accelerating with the friction. This is on chain. What's also on the blockchain is AI. So this sequence is not driven by me pressing the keyboard and mouse. This movement is driven by very simple AI, where it basically manipulates the input queue. If you play a fighting game, you know what input queue is. So this is a game about AI fighting against each other in a fighting game context, and we are not announcing this title yet. There's a lot to be done here, but I think that this tech demo sort of signals at the massive unrealized potential of making games on Starknet. So thank you, and happy to answer any questions.
Thank you for your speech, and now we're going to have some session for questions. So is there any questions? I'm going to transfer the microphone. Then I'll just read out 2 questions in the YouTube. First question is, why should I learn Cairo if there is already a Solidity translator?
Well, my experience is I don't have much experience in Solidity. I like Cairo because it's a very low-level language, so it gives me full control. And I like to have full control over whatever I program. So that's one reason to learn about Cairo. The second one is I don't think the transpiler will give you the native performance of Cairo. If you were to just learn Cairo, you like systems that have high performance. If you rely on translation, there are a lot of language features that are not supporting Solidity, and so there's no way to map from one language to the other. So writing Cairo gives you the best performance.
Thank you. And there is one more question. What is the ticker for topology? What is the ticker for topology?
Oh, we don't have a ticker. We don't have a token. I think we're really building for a long term. We're speculating game 2.0, and this will basically offend the game industry. And so it's way too early to talk about token.
Thank you. Um, so now we're gonna move to the next session. Thank you for your speech. Before to move to the next session, I'll ask for keep the volume down during the speech because we are also delivering the speech through YouTube stream. So it'll be better to keep silence during the speech so that everyone can hear clearly. In the next session, Ellie from Software is going to talk about Starknet. So please welcome Ellie.
I can just stand here and do I use it?
Oh, yeah, here is the.
Okay. Check out the the screen. What's it called? Screensaver. Oh wait, but I need to probably do this. No. No, not this. Okay, so how much time do I have to? 20 minutes? Okay. 20 minutes, okay. So, hi, I'm Eli Ben-Sasson. I'm with Starknet. I'm co-founder and president there. And I want to tell you a little bit about, just give you some feeling for the moon math that goes into Starknet. So I'm not going to explain how to program in Starknet or how to deploy on it. There are bigger experts like Ben and Gilti Gioza and others. But I will tell you a little bit about why it is that you have this magical scale from it. So just very briefly, Starks is a cryptographic and mathematical technology that was, it's the culmination of 30 years of research, often called moon math, in areas of computational complexity and cryptography. And what Starks do is they prove integrity. And what that means is, it was beautifully defined by the author C.S. Lewis, integrity means doing the right thing even when no one is watching. So Starks are a technology that let you know that someone else was doing a computation the right way, as if you would have executed, as you would expect this other person to execute in the right way. In particular, if you're processing transactions, right, then doing so with integrity means not taking all of the money and putting it in your account, but like only when there are signatures, updating the accounts correctly. So Starks is a technology that gives you that. And but this is like a lofty idea. It was a bunch of math theorems and things like that. And in order to make it into products and things like Starknet, and then having people, talented people like Gilti Gioza and others, that building things on top of it requires a lot of work, ongoing work, and that's what we do at Starknet and what the Starknet ecosystem is doing very successfully. And all of this hard work gives you the ability to scale Ethereum today by orders of magnitude. So the StarkX standalone systems and Starknet have been processing more transactions, more volume, and at lower cost than all of the other L2 technologies combined. So now I want to double click on the moon math and tell you a little bit about the magic that underlies it and what's going on there. So here's an amazing fact that we're aware of, but I still want to just say it explicitly. So when you run a poll, right, let's say for an election, it turns out that the margin of error depends on the number of people you ask or the number of samples you take. It does not depend on the size of the population. So what I did here is I went to some margin error calculator online, and here I said, what is the margin of error when I sample 1,000 out of 1 million? It's 3.1. And if you take the population and make it this large, but still take only 1,000 samples, you still get the same margin of error. So there's something about statistics and probability that let you get a very good handle on a result with a very small number of samples. And the amazing revelation that underlies the moon math that is Stark's is captured by this beautiful theorem from the 1990s, which says that the same phenomena that of margin of error depending only on the number of queries, the same phenomena holds when you're polling not just the elections, but also when you're polling the question, which is the computation being done valid? Has it been performed with integrity? So you can poll this problem and get a very good handle on the margin of error, which is independent of the size of the computation. And there's a small caveat. Okay, let me just spell it out again. If I take 1,000 samples, I can know with, let's say, a very small margin of error, whether all pieces of computation were done correctly. And this holds if these were 1,000 transactions, 1,000,000 transactions, or a Google many transactions, right? And this is what the PCP theorem says. So it assumes a certain assumption, which is that the execution trace of the computation be written in some nice format. And actually this nice format is very mathematical in nature. You take the execution trace and you have to encode it using evaluations of low-degree polynomials over a finite field. So a lot of math terms there, which I won't go into. And this beautiful revelation was already known 30 years ago. I just want to quote one sentence from an amazing paper from 1992 by Babai, Fortnell, Levin, and Segedi that says, in this setup, a single PC, right, this is the 1990s, PCs and supercomputers were still, things that they didn't have smartphones and blockchains. But they say here, in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. So they said, here's a math technology that allows you to know, using a very weak computational device, that a possibly malicious, extremely powerful, bigger device operated with integrity. And the problem in the 1990s, and the reason you didn't grow up seeing this technology deployed, was that it wasn't scalable. There weren't enough. If you want to take this math and make it into a system, you'll find out that there are not enough atoms in the solar system to write down this format. And then so prior and leading up to Starkware, what I did was research with a lot of colleagues, and when I was doing my postdoc at MIT, this was a eureka that I had with Madhu Sudan, who was my host there, which I'll just translate it to more human language. Now we knew how you can write these proofs in a way that there are barely enough atoms in the solar system to make it to make it fly. And with a lot, this was 2005, and with a lot more work and several more publications, just before we started Starkware, we knew that by now there are enough atoms, even on a laptop, in order to write down one of these proofs so you can verify them very efficiently. And this is like the origin story for Starkware. By now, Starkware has, its mission is to give you integrity through math at scale. We invented a whole bunch of technologies that are used by now, Cairo, Sharp, Validium, Volition, Fry, and Stark, and others. By now we're more than 100 team members, and we raised $250 million in equity over several rounds. And I want to now just explain a little bit, give you a hint as to how you get this magic. How can you do this polling of a integrity of a computation? So, and here I'm continuing something that I believe Ben already spoke a little bit about. So here's a claim of integrity. Someone claims the following, starting from a state of accounts whose hash is X, I process 10,000 Ethereum payments using program P. So the program P just specifies what is a correct processing of transactions, checking the signatures, updating the account balances, and so on and so forth. And the hash of the new system is now Y. So the system is now parameterized by these 4 parameters, the starting state X, the end state Y, the program P used to process it, and the number of transactions. And here's an intuition for how the PCP theorem, this magic, works. It turns out that you can take this statement and convert it into a Sudoku-like puzzle. So if you know Sudoku, right, it's you get this board and some numbers are filled out, but you need to fill in the remaining positions in a way that a whole bunch of constraints applied to small pieces of rows and columns are valid, right? So that's the challenge. And it turns out that you can take from any such quadruple, X, Y, P, and T, the number of transactions, you will get some Sudoku-like challenge. So the way the proof works is that basically the verifier side is expecting the prover to fill in a correct solution to the Sudoku-like problem. Now, the cool thing is that the prover needs to process the 10,000 transactions and then record it in a certain format, which is the way you fill up these blank places in the Sudoku challenge. So the prover works a lot. But, and here's the amazing part, remember, like in polling, right, you only need to make a very small number of samples. So in this world, the verifier now only needs to sample a single constraint, a single row and column, and just inspect it. And that's it. That's the sample. So just like when you sample a population, you're not going through all of the population, you just take a very small sample. Here the analog is, you pick a random row, let's say this one, and you open up the entries here and you see if they match the constraint system. That's what the verifier does, and that's how you get efficiency. And the really amazing thing, there are a lot of magical parts that underpin this. One is that even though this is a pretty large Sudoku table, and I forgot to say that a Stark is almost the same thing. The difference between a PCP and a Stark is that in a Stark, actually, you construct the board over several iterations. So first of all, the verifier sends over the first board. The prover fills it up. Then the verifier tosses some coins and generates a second board, and the prover fills it up, and then you do this a number of times again and again. So that's the only difference. Now, the really magical part is what is specified here, and it should sound a bit impossible or too good to be true. First of all, when the verifier sends the challenge to the prover, the Sudoku, it doesn't send this big board and like with all entries, no. It sends information in a very succinct manner that the prover knows how to open up into this board, but the verifier never needs to open up this board. Moreover, the verifier, when she comes and samples a constraint, and by the way, these are sort of three-dimensional constraints. Some of the constraints go through several different, these Sudoku challenges. When the verifier samples a constraint, again, she doesn't need to open up everything. She can just take the information X, P, Y, and number of transactions, and very efficiently generate a constraint and know that here there's the number 7 and here there's the number 6, and let's see for the rest, let's just check the rest of the numbers. So there's a very succinct way for the verifier to both specify the problems that the prover needs to solve and to check them succinctly. Another statement is that if the prover is honest, if indeed the result of processing these transactions moves you from state X to state Y, the prover can generate efficiently, very efficiently, in nearly linear time, a way to fill up all of this information. And the most magical part is that if the statement is false, any which way the prover tries to fill in this pattern will lead to 99.99999 many nines after it, constraints being falsified, which means that by inspecting a one random constraint with extremely high probability, the verifier will know and see that someone tried to cheat. Okay? So now, all of these statements are proven math theorems, okay? But of course, explaining them takes several courses of advanced computational complexity, so I won't prove it to you, but the white papers do appear out there. Now, here I just want to tell you a little bit about additional resources. So, there's a very brief explanation of the magic of Starks, which is if you just go to starkware.co/stark. And it actually is a point where you can get more information from it. If you want to read a slightly more detailed explanation about the math and how it works, there's a 5-part Medium blog. And you can also Google just Stark Math, The Journey Begins. And the last resource, so I've been running this Stark at Home YouTube series, and especially the first 7 parts drill down on all kinds of math-related questions and explain how this works. So just summarizing, what I wanted to do in this brief period is like to peek a little bit under the hood of what is this magic that allows you to scale Ethereum so well. I'm happy to answer any questions. I think I spoke only for 15 minutes, so happy to answer questions. Yeah?
Can you elaborate more on the sampling method that you mentioned about verifiers?
On the if I can elaborate more on the sampling method. The sampling method it's like, the whole thing has to be opened up in order to explain what is the sampling method. So I'll say a little bit about how the Sudoku challenges are generated. The prover is supposed to take the execution trace and then apply an error-correcting encoding to it using low-degree polynomials. This is known as Reed-Solomon encoding. Okay? So you take the execution trace and you apply this encoding to it. Then there are certain constraints. So think about like the execution trace as the sequence of Cairo steps, it could be, right? One after the other. And what the prover does is that right, each step should follow logically from the previous state, which means that it should satisfy certain constraints. And these constraints turn out to be low-degree polynomials. So the prover is supposed the first Sudoku sent is actually just the execution trace encoded. Then the verifier succinctly, so the verifier has the constraints that specify, let's say, a Cairo program. Now, the Cairo virtual machine specifying its logic requires only 50 polynomial constraints of degree 2. So what the verifier now does, it samples a random linear combination of these 50 constraints, and now it's one constraint that is sort of a mixing of all of them. And this is the next challenge. The prover now fills in the next Sudoku challenge, which is apply the constraint, which is randomly picked, to the previous state. So you get some polynomial map of the previous polynomial to some new set of polynomials. Then the next challenge arises from taking a random linear combination of all of these rows and applying a separate protocol that is like a folding of an FFT. It's called the Fry protocol, the Fast Reed-Solomon IOP. And it itself is interactive. There are several rounds. Okay, so now to answer your question, what does the verifier sample in the end? The verifier samples a little bit of all of these things. It samples some Fry constraints, which are random linear combinations of some of the elements. And it samples some of these polynomial constraints that come from the program. And that's, I don't know if I clarified it more, confused it more, but that's the best I can try to give an intuition for what is the sampling process. Yes?
Keep compare Snark with Stark. Snark. In Snark, N stands for non-interactive, and I'm wondering that you just gave me an example of like stock group, and in stock group, verifier would be some contract in L1, and prover would be a sequencer in Starknet. And is there any real communication between them? For
Yeah.
and I'm wondering that Stark is not interactive or not interactive. I'm wondering.
Terrific question. So you're right that Snark is non-interactive, and I presented here the interactive version of Stark. Now actually on Starknet and the Starknet systems, we submit non-interactive proofs. The way we do it is we apply something known as the Fiat-Shamir transformation, which basically, Stark is, the T stands actually for transparent, which means that all the things that the verifier sends are just random bits. So the Fiat-Shamir heuristic allows the prover to simulate this verifier by basically taking a hash of its previous messages and sending that as the next verifier message. So you can take, all this to say that you can take interactive Stark and make it non-interactive using the Fiat-Shamir heuristic. But to answer your first question about the difference between a Stark and a Snark, the bigger difference is that, especially, I'm referring now to the pre-processing Snarks with a trusted setup, so you can still use this explanation to tell you what a Snark does. What a Snark does is that there's a pre-processing phase in which this whole thing is opened up and a single constraint is already sampled in the trusted setup generation phase. And then what the prover gets is a whole bunch of keys that allow the prover to fill in this one constraint, but in an additively homomorphic preserving way, meaning that the prover does not know on which point it is, which constraint it is filling up. And the pre-processing or the toxic waste comes from this process of selecting randomly a single constraint and filling it up and generating all of the information needed for the prover to run through it. So that's the difference. And in Stark world, we don't require that. We just tell the prover, please write down the whole thing. It's very transparent. That's why we are post-quantum safe. We have no number theoretic assumptions. We don't need elliptic curves or pairings or things like that. It's basically we do a lot more math. It's work harder to prove the soundness in this more transparent world. That's the big difference. Yeah, yes?
So in this interactive version,
Yes.
it's a security technique per round.
Yes. The question is, in the interactive world, is there security per round? Yes. So when you go to the soundness analysis, there are two types of errors. One is the interactive error, interactive phase error, and the other is the error that comes from the query phase when you actually sample. And it actually turns out that we can provably show that the interactive error of sampling randomness is very, very low. Like, provably, it's like, if we're using a 256-bit field, the soundness of error per round is something like 1/2 to the power 250. Very small error. And we do this like 3 or 4 times, and it's additive accumulation. So this is minuscule error. The huge error, relatively speaking, comes from the query phase. We actually need to sample more than one constraint. We could work with only a single constraint, but it's more efficient to sample a few. And the number we need to sample is because the error in the query phase is actually significantly higher. It's pretty much the rate of the Reed-Solomon encoding. So if you use we use rate of 1/16, you get roughly 4 bits per query of soundness. So we need to repeat it like 32 times or something like that. Yeah.
How long does the query take?
How long does it what?
The query take.
The query is you open up the Merkle branch, you just display information and also verifying the queries. The big bottleneck is generating the proof. Do a lot of FFTs or refined fields, memory guzzling stuff. Checking the proofs is very fast. The whole verification process takes between 1 and 3 milliseconds in a single thread. I think my time is up, right? Long ago, no?
I would like to ask one last question
Yeah.
from YouTube stream. I think block creation time is quite slow in Starknet. Why is that? And will it be better in the future?
Okay, the question is that the slow computation time on Starknet, and will it get better? So yes, that's true. The phase that we're now focusing on is increasing throughput. I want to say that this is, okay, whenever you scale a system, something's going to be your bottleneck, okay? Our bottleneck right now is not in the proving technology. There is a sequencer, which has a Cairo runner in it, and it's not very fast currently, but we're making it faster. And when I say we, I want to stress, it's not just Starknet. I don't know if you saw that, like on Twitter, like amazing like tweets from like 2 days ago. The Lambda class team from, I think they're in Brazil, have a Rust Cairo machine that is 100 or 140 times faster than the Cairo machine we're using. So the bottleneck that people are experiencing is related to the sequencing process that we are now, actually some of the next upgrades are going to make it slightly more parallelized and increase throughput. But the long-term answer is yes, it will get tremendous scale.
Thank you for great speech, and I think we're gonna move to the next session. So from now on, we're gonna you will able to learn developing language of Starknet, which is called Cairo, with one of the best contributors of Starknet ecosystem. The session will be about 9 minutes long. We're gonna have a short break between the sessions, and please welcome Trial.
네.
So we're gonna start at 4:55. Please come back at 55. Now we're gonna have a workshop on Cairo, so please read it. And please be quiet because this session we're gonna have sessions through online. So I'll appreciate if you can keep the volume down so that you can hear clearly. To start the session, everyone please be seated and please keep the volume down.
음식을 꺼달라고 얘기해. 근데 먼저 두 분이라서 조금 더 따가워 보이는 것 같은데. 데이빗 먼저.
all hear us. It's been Can you hear me now? Is that better? Hello? Testing. we're getting a bunch of background noise, but I can hear something coming from your end. I'm not sure if you're trying to speak to us. Maybe shoot us a message in the chat if you are. It's pretty tough to hear.
요 주변에서
Yeah, hey, is that better? Are you able to hear us?
마이크 하나도 없어.
Sorry, we had a video issue and now we just solved it. So everyone now we're gonna start our session. So please be seated. There is an announcement. Now we're gonna start our workshop session. So everyone please be seated.
저희 이제 다음 주제 시작하니까 앉아주시면 감사하겠습니다.
Since we're gonna do this session through via online, so everyone this time please reduce your voice, keep your volume down so that everyone can hear clearly. Thank you.
Can we start now?
Okay, thank you very much. Sorry for all the technical difficulties. Can you just shoot a message if you can hear us, because it's a bit tough to hear what you all are saying with all the background noise. Is our audio clear? Okay, I will share my screen. Can someone enable screen sharing? One of the hosts enable screen sharing for me? Sorry, not sure if you guys could hear me on that one. Could one of the hosts enable screen sharing for me?
화면 공유 권한 넘겼나요? 화면 공유 권한. 공유 권한. 안 되나요? 됩니다, 됩니다.
Okay, fantastic. Okay. Okay, hey everyone. We are, myself, Mikey, and Matt are the co-founders of Triality. We will be taking you on the journey of creating a Cairo contract all the way through building your web app on Starknet.js via Next.js app, and kind of walking you through that whole process. So for any new devs or experienced devs, hopefully we're able to give you some pretty interesting tidbits of information, kind of go along the journey together. If possible, could you guys mute the audio on the other accounts? It's ringing a little bit. Thanks. Okay, yeah, so today we're going to be doing a Cairo Learning 101 with our team. So today for the demo, I'll give a quick intro about what we'll be doing. We're going to be creating Cairo contract, testing the Cairo contract, deploying that Cairo contract to testnet. We'll be viewing and understanding that contract in Voyager. We'll set up a Next.js application and connect to the contract via Starknet JS and or Starknet React. We'll do a little bit of comparing and contrasting between the two front-end frameworks, Starknet JS and Starknet React. And then we will play the game that we're making in the contract. So for a little background, we wanted to give somewhat of a comprehensive demo. So the game we're going to make is as follows. We will have an owner of the contract who's the only person who's able to update a number that is viewable to anyone on the internet. And basically what's going to happen is it's going to be a number with several digits. The goal of all users is to try to guess the sum of the digits of that number as quickly as possible. If they're the first person to be able to guess the sum of the digits, they'll get a point and we'll continue, and then only the owner can update that number. So if the number is 123, that would be 1 plus 2 plus 3. And we're basically going to implement this entire thing for you, show everyone, especially new folks, that Cairo is not too bad. And the Starknet ecosystem has built already a lot of tools and is continuing to build great tools around building web apps and deploying contracts not so bad. If you want to follow along, I'll leave this up for a second. You can pull down our repo from this GitHub link, and you can pull the code, follow along as I'm coding the contracts, as Matt's coding some of the front end, and get a little bit more of a sneak peek into what we're doing. And you can even follow along with the README. You can do everything that we're doing if you're a little bit more advanced as well. Okay. All right, it's coding time, so let's get started. So, like I said, we're basically going to go through the entire process of what it would take to first build, test, and deploy a Cairo contract. So I'm starting with a totally blank slate, a Visual Code Studio window with nothing in it, just 2 folders, a contracts folder and a test folder that I set up earlier. Okay, sorry, it looks like I'm having an issue. Let me reshare. Okay, so back to what I was saying. We just had a Visual Studio Code window. All we have is 2 folders, super bare bones. Anyone can jump in if you have Visual Studio Code if you want to try to tag along while we're doing this, but I would recommend just watching or pulling the video if you want to follow along with the code. So what I'm going to do is I'm going to create a new file. I'm going to call this demo.cairo. This is going to be our single Cairo contract that we're going to write for the duration of this course. And since we're going to deploy this onto Starknet, we need this indicator at the top, lang Starknet. You have to put this at the top of any Cairo contract that you want to deploy as a Starknet contract. And then we will start with some common patterns of building Cairo contracts. So let's say we want to set a storage variable. So we want to store onto the blockchain a felt, which is in Cairo similar to like an integer in most programming languages. Won't go into the nuances there. A bunch on it in the Cairo docs though. So in order to store what the current number is of the game that we're going to play, let's write a comment first. So comments are started with the pound sign, and then you can write your comment just like in any language. So let's stores the current number some digits. So every storage variable we need to use the decorator storage var. And then the pattern for creating a storage variable is you'll call a func, and then take in the inputs and provide the output. So in this case, there's no inputs for the current number, so I'm going to call this function current number. It's just you're going to be able to read the current number, which is a single file, and you'll be able to write the current number, which is the single file. So the syntax looks something like this. Semicolon at the end. So this denotes the syntax of the function. This is saying that this output argument is a felt, we're calling it res. And in order for us to be able to actually get what is in this current number, we need to get a @view method. So we're going to use a different decorator. We're going to declare a new function called getCurNumber. And in here, let's see what happens if we would, sorry, just moving some stuff around, if we try to just call it with, as a normal function with we'll get into implicit arguments. So in here, what we want to do is we want to read the current number from our storage variable. So how we do that is we need to unpack the value. So whenever you're reading the value of a function in Cairo, you need to make sure you put parentheses around the variable that you're declaring. Otherwise, you'll get an error, and we'll see that later. We'll go through that. You use this current number .read, so that allows us to read what's inside of this function and what's stored in the storage variable. And then let's return in Cairo, you don't have to, but it's good practice to, in your return statement, use the name of the return and set that equal to what you're returning. So for this kernum is referencing this, and this kernum is referencing the variable itself. I could change this, and we'll look at that later. So if I try to compile my contract, let's just quickly do that. Start seeing what some errors look like. So we get an error very quickly that we're missing an unknown identifier. This is called pointer. And just to point out that Cairo is still quite a young language. In order to make the compiler happy, you have to use the implicit arguments for a lot of these functions, especially in Starknet contracts. So we won't take too much time to go through, but a quick overview is that implicit arguments are arguments that are passed inside of these curly braces before the explicit arguments that are passed inside the parentheses. And in the case of these view functions, you need to pass in a syscall pointer, a Peterson pointer, and a range check pointer. If I compile again, we should get another error, which shows that we don't have we have this unknown identifier hash built in. So I'm going to import this hash built-in from the Cairo Common Library. So this is the general syntax for importing. You'll do from the library you want to import from, and then import the identifier or the function that you're looking for. So now, finally, if I compile, finally got a successful compile. So for everyone following along, great work. We've officially added our first storage variable to a Starknet contract, and we've added the view variable to be able to view this card number. Okay. So I will add a bit of comments here, just for good practice about this function. And then let's add our constructor. So the constructor is the method that's going to be called when the contract is deployed. And I won't type this whole thing out, but I'll just copy and paste from the code that we have and we can walk through. So we're using this decorator at constructor to define that it is the constructor. And we have similar implicit arguments that have to be passed in. And in this case, we're going to pass in as well a single parameter such that we can set who the owner of this contract is going to be. So the rest of the storage variables that we're going to need are going to be, in order to make this compile, are going to be an owner and an is active, because we're going to make it such that only the owner can overwrite the current number. No random user can do that. So in order to get there, I will is that better? Okay. Getting some comments to make the code a bit bigger. Hopefully that helps everyone see. Sorry if it was tough before. Yeah, so I'm going to do a bit of, we need to get in order to make this code compile, we'll need to make sure we have our owner variable, which will be a storage variable, and we'll need our is active variable as well, a storage variable. So I'll get our owner and plug this in. And so very similar to this current number, you can see this syntax is basically the same. We're just, again, storing a single felt and as a storage variable, and then we'll also need a is active storage variable. And this is active is really like a Boolean, but in Cairo there's no Booleans. You just use a 1 or a 0. So we'll actively manage that, but it's pretty simple. All you're managing is numbers. So in some ways it's nice, in some ways it's tricky. So now that I have all these storage variables, I should be able to test that I can kick off my my whole program via a test. So let's copy in a simple test and analyze it a little bit. As with any good practice, you should test your code as you go. And we probably won't be so good in this demo the whole time, but to start, let's try it again. Okay, so I'm going to do some imports. A bunch of documentation is online for how to set up your Python tests. I do a bunch of imports for Python and a bunch of imports from Starknet libraries. And then I'm just going to declare a couple of addresses, and then we're going to use this @PyTest async IO fixture, which is basically called before every PyTest is run. And what it's going to do is it's going to deploy, not actually deploy, but deploy the Starknet contract, and then return that contract for us so we can interact with it. So let me save this. And we can enter our test folder, and then let me grab command for running the PyTest. So it looks like we're getting error. We need to set our getters for each of these. So let me copy this in so we can get, so similar pattern as we have to using cur number, we need to be able to get owner and we need to be able to get is active. So both of these will look pretty much exactly like cur number, just with a different function name. So I'll just copy these in so you don't have to watch me type very slowly. Just again. Cool. So we're getting that our test is now passing. And if we have a look at what our test is doing, basically what we've done is we've run our deploy of the contract. We call to get the value of is active, and we call to get the cur node. And you can see in our constructor, which runs on the deploy of the contract, we have the fact that is active is 1, and the cur number is 1, 2, 3, 4. So far so good. Let's move on to a bit more of nuances. So a couple of other things that we need for our app. We want to know who the last winner was, and how many wins an address has. So the last winner is also, thought I saw a chat, but I think I was wrong. The last winner, again, is super similar to these other storage variables. I'll copy this in. Because we're just storing one felt to storage. And, okay, I heard that we want the code to be bigger. Is that better? Yeah, that's good enough. Does that look good, Matt? Okay. Okay. So now we've added the storage variable last winner. It's similar to all the other ones, so I'll also copy over the getter for it. So this is kind of the common pattern that you have to do for your storage variables is you create your storage variable and then you need to create your new decorator, your getter for it, that storage variable. And then lastly, we're gonna implement the wins by address. So the wins by address is a bit more nuanced because instead of just storing a number, we're actually going to be storing a number based on the mapping. So based on an address, we'll store how many wins they have. So let's see what that would look like. Let's do that. Storage variable. So same decorator. We call it function wins by address. Address, take felt, call it address, and we will have a mapping to the input is a felt, which is the address, the output is the num correct. And the rest of it should look pretty similar. So just now we are taking an input when we do a read, as opposed to, you can see when we do when we do a write or a read. We're taking we'll take 2 inputs when we do a write, and we'll take 1 input now when we do a read. For these other ones, when we do a read, there'll be no inputs because you can see here when we do the at view, there's no inputs. So in order to implement the getter for the wins by address, so similar, we have our view decorator, we have a function with all our implicit arguments passed through. This time we have an explicit argument passed in as well, which is the address, which is the felt, and based on that mapping, we will return the number of wins by reading the storage variable. Hopefully that all makes sense. So let's compile, make sure our code is all good. All good. So now we have done basically all this setup that we need for the storage variables and for getting all the storage variables in our constructor. So next, let's start implementing some of the core logic of the actual contract that we want to write. So there's really two things that we want to do. One is we want to be able to verify the sum as it's passed in to our contract and see if the user is able to sum up the digits correctly. And the other one is we want only the owner to be able to update the current number. So let's start with the updating of the current number. So first we'll need an isOwner function to tell if the person calling the contract is the owner. I'm going to copy in the function signature with some comments. So we will get whether the calling address is the owner of the contract, return 1 if they're true, return 0 if they're not the owner. And how we'll do this is we will use a method that one of the Starknet libraries provides for us. It looks like this. So we'll let caller be equal get caller addresses. So this is a function that we'll have to import from the Starknet components calls, and this will give us the address of the user calling this contract. From there, we need to define who the owner of this address is as defined in the constructor. So we'll do owner.read. Remember, since its owner is just a single felt, we're just using the storage variable to read from it. We don't need to pass in any parameters. And then we'll say if caller equals owner pattern, return is owner is 1, and if else return is owner equals 0. So let's break down this function, what's going on. We've set up the our initial two variables, caller and owner address. This is the syntax for writing conditionals in Cairo. You use an if statement, and you can use the double equal sign for checking equality. The Cairo team has a math library that we will see later that will use at least one of their functions. But out of the box, you can use this equals equals for equality like many other languages. And then we'll just return 1 if this is the case and 0 otherwise. And then in order to update the current number, we will have to use that function. So let me copy over this method signature with some comments. So we'll update the current number that users will try to sum the digits, and we'll have one argument passed in, explicit argument, which is the updated number that the user will send over. So let's see how we would implement this function. So this is a function that's going to be blocked for any user who's not the owner of the address. So building some security around it. So say let owner bool equals is owner, the method that we just created. And a good practice in Cairo is if you're going to run an assertion to make a function fail, you should use a with adder block so that you can write a verbose string message that makes debugging a lot easier. So we'll do that here. So I'll say with adder error message. This game is not active. And again, we'll create this block. We'll run an assertion, so you can use the keyword assert. So if someone's trying to write the current number, we know that they need to be the owner. So we need this owner bool to have been returned true. So we need to assert that it equals 1. And then here. And then if we get past that assertion block, we need to write that the game is now active again because they've reset the new number, and we will then write the new number to the storage variable. So let's do that really quick. No. Cool. So let me save this. Let's compile. And it looks like we have an issue, which is that this error is basically saying every function needs to end with a return. So I just missed return statement. We don't need to return anything because we're just updating the number. Perfect. All right. So let's bring in a couple of other tests. So just through. Here we go. So the two tests that I'm gonna add to our testing file now are going to be setting the current number with an admin. So the admin address is going to be 654321, who is the person who deployed the contract. And then we'll also try setting the number with a non-admin, and we should get an error. So we'll have to run this with PyTest raises the Starknet exception. So let's run our tests, see what happens. And to what Ellie was saying, I think there's a lot of improvements coming in terms of the speed at which a lot of things will be compiled, and a lot of the development tools are getting better and better, especially with people working on Rust as a primary platform for a lot of what we're doing. So we can see that the 3 tests passed about 10 seconds, but so far so good. Our contract is looking pretty good. Our last bit that we're trying to do is verify the sum of the digits. So we can create a verify sum, and I will copy over this function that we've created. Basically the skeleton of it, and we can talk through it. It's a bit long. So you can see in the update here now, we're going to go through this, but since this is a function that can be updated from outside of the contract, so someone calling into the contract, we use decorator at external. Similarly, for verifying the sum, this is when someone's going to be, guessing what the sum of the digits are. Externally, so we pass in this external decorator, and we pass in a user answer, and we'll return to them whether or not they're correct. We start with alloc locals because we will be using local variables. So in Cairo, not to go too deep into it now, but you can initialize variables in several different ways. You can use this let keyword, you can use locals, and you can use temp bars. Each of them have their own unique use cases. The locals are typically amongst the community known to be the safest because you get the least number of revokes. So often if you use a let or you use a temp var and you use that temp var in another function, oftentimes your variable will get revoked, but it doesn't happen as often with locals. So oftentimes you'll see people just using locals most frequently. And feel free to shoot us more in-depth questions about that later. After that, similar to the assertion we wrote above, we will use the with adder message block. If the user is trying to verify the sum and the game is not active, meaning this assertion fails, then we will return, and the user will see this message: this game is not active. Next, we'll read what the current number is, and then we will use a magic function that we'll write after this to determine what the actual sum of the digits is in Cairo using recursion. And we'll find that if the res that we get from this magic function that we're going to assume now is correct equals the user answer that they pass it in here, then we will find the caller address. We'll write that the game is no longer active. We will read the number of current wins that this address has, and then we will write their wins with an updated +1. So if they had 0 wins, now they'll have 1. If they had 1 win, they'll have 2, etc. And lastly, we'll write the last winner, the person who won this game last, was this caller. And then for our front end, we will return that they were correct. And obviously, if we don't go inside of this conditional block, then we will return that is correct 0. So the last bit that we have to do is implement this find some digits. So I will copy over this method signature, and then we can go through writing a recursive function in Cairo together. So the goal of this function is to be able to take an input, say 1, 2, 3, 4, and then add the sum of its digits, 1 + 2 + 3 + 4. And the question is, how are we going to do that? Okay, so let's create our base case. If our input num is 0, we will return our current sum. And you can see we pass in our current sum to start as 0. This is because whenever you return a value from a function, you need to wrap it in those parentheses so it can later be unpacked. Everything has to be a tuple. Now we will get comment. So we need to get our unsigned remainder by dividing it 10. And this will be just the ones digit. So if you took, 1,234, 1, 2, 3, 4, and you divide by 10 with a remainder, the number you get as your remainder is 4. So that's the first number that we're going to start adding to our current sum. So to do this, we're going to need a function, which first we'll write this out. So we'll get Q and R, the quotient and the remainder, and we'll use unsigned div rem of input num. So this is basically saying take the unsigned division and give us a remainder of input num divided by 10. This is a function that the Cairo Common Math Library has given us. So I need to import that up here. And now that should be functional. Next, update the current sum by taking this remainder and adding it to the current sum. So let's say per sum equals per sum plus odd. So we'll be using this this variable that came back to us from this function, and this is the remainder. So this is 4 in that first iteration, and then we'll say give a comment to this.
Recording stopped.
Yeah, I can share the video. Can you all hear me now? Good to go? Okay. Let me know if I'm not good. It's late here in California, so bear with us. So we got very close to finishing up this contract. We're just inches away. So sad time to get cut off because we were just there. So let's finish up where we were. So basically we had added our sum to our current sum to the remainder, and then what we need to do is basically knock off that one digit so we can recurse and keep making the input number shorter. So what we'll do is let updated input equal input num minus r, so that'd be in this case 1,234 minus 4, and then divided by 10. So we're just chopping off that one digit. Then we will recurse now. We'll get the res equal to find some digits, which is the function that we're in, and pass in up input and updated. And from there we can return res equals res for the method signature. So now we have all the functionality that we need for our contract, because going back through, we're able to verify the sum by using this recursive method to find the sum of the digits. And in the case that we get it right, we're able to update all the storage variables correctly, and we're able to update the current number if and only if you are the owner of the contract. Let's compile our contract, make sure we haven't broken anything too bad. Okay, great, no issues. And then let's add a couple more tests to this. So one of them will be a test for what happens when the test, the check is correct, and Hey, sorry, we had a quick internet drop. Hopefully you can all hear me okay. Before I went, I was just saying that we're now able to basically test correct guesses, test incorrect guesses, and update the correct number. And lastly, all that passes, we have a couple of other tests, but we can continue here. So now that we, oh, I don't think I'm sharing my screen. Okay, now that we've done all of that, what's left? We've now created a Cairo contract, we've compiled it, and we've fully tested it. Now it's time to deploy. So, this contract, let me set our network. So I'm going to set the network to Starknet network equals alpha girly. If you want to deploy to the testnet, you should always set this in your entire environment. And then I will deploy the contract and test it on Voyager. So one quick thing to note is passing in the circuit deploy, excuse me, it's going to be reading from this this demo compiled JSON, this one at least, right? And we're passing in a single input. This input reflects this input in the constructor, so the owner address. And you can pass in multiple inputs here, but in this case, I'm setting myself as the owner address, so if Matt's in the game, I will be the only one who's able to occupy. So let me deploy this, and boom, you can see the deployment transaction is successful, and we now have a contract address. I will send this over to Matt, and he'll do some exploring on Voyager, and he'll use this to show us how we can connect to the contract with a Next.js app and have some fun in the UI. So, Matt, if you want to take over.
Yep. Thanks, Mikey. Okay. Send it over. Yeah. All right. So we're just gonna copy the contract deployment address that Mikey just sent, and right now I have a skeleton of a UI webpage, basically, and our goal here is going to be write a very simple UI. Nothing too fancy that can connect to this contract, read from it.
Hey everyone, hopefully you can hear us. I think there's just some connectivity issues. Matt's rejoining as well right now. Apologies.
Screen out. So basically the idea here is to just build a very basic UI to talk to our contract. So I've connected, take a look at the contract that was deployed by Mikey to see if it's available now. So it is, okay, so now we can see, looks like I have 20 minutes left. We can read the getters that might be added to the contract. We can see what the current number is. We can see which was 1, 2, 3, 4, which was the default when it was created. We can see if the number, if the game is active, when this is active pool. And we can see get number of wins if you paste your address. So I'm connected to Bravos here, so I can just paste my address in here. And I don't have any wins right now. So let's just try to build a very simple UI quickly to read these values and write the values. So I'm going to be using Starknet.js, which is a great community. That you can use JavaScript to make a functional better. Alright. So the first thing I want to do is implement a connect wallet function. So this button here to connect the wallet will actually do something and pop up the Origin or Bravos selector. So I hit Starknet from the again package, and I've defined a Starknet window object here that we're going to use to interact with the contract. So I'm going to, this is going to pop the wallet here, and well, whether or not I want to show the pop up. So if I have the Starknet object connected successfully, I'm going to enable Starknet.enable and enable the Starknet object here. And then I'm going to just set the address that's connected locally. I have a React state variable. Set the address to starknet.account.address. So let's save that, and hopefully now the connect wallet button is all linked up to Starknet.js, and we can choose a wallet that we want to connect. So I'm going to connect Origin X here, and then we can see now my Origin X wallet account is connected and being displayed in the UI. So the next thing we want to do is start reading some values from the contract. So I have a function here called read game state that I'm going to fill out. The first thing I'm going to do is I'm going to say num response is Starknet.account.call contract. So I'm going to be using the call contract function here of the Starknet account object, and I'm going to give it a contract address to call. So this is the one that Mikey just deployed. I'm going to give it an entry point, which is the function that I want to call. So in this case, the get current number function. And finally, any arguments. And this one doesn't take any arguments, so the call data here is going to be just an empty argument. Then as a second argument here, I need to give what is the block identifier, so which block I'm pulling from, and I'm just going to say I'm going to pull from the latest block. So once we have this, we can parse it and show it in the UI. So we're going to set this current number state variable that I have in React to parse the integer that comes back from the chain. Comes in as like an array, as a object with a result. To string that, it should in effect. So this function is being called. And now we can see we have this number 1234 that's being pulled from the chain using Starknet.js. So I'm gonna just repeat the same process for the following 3. I'm just gonna copy paste it in the interest of time here. So we're gonna do the same thing for is active, last winner, and my number of wins. So we need to define this call contract method, which is going to, basically the format of all of these calls look pretty much the same. I'm just changing which entry point, which is which function in the contract I'm calling. So I can just define a helper function here that's just going to give me, it's going to give me a little bit of code to clean up. So, let's call this. There we go. It loads. The internet's a little slow. Hopefully, we should be able to see this value. There we go. All right, it's being read. So, last thing we want to do here now is actually write to the contract. So, execute a transaction that is going to call the verified sum to win the game, basically. So, what we want to do here is use the Starknet executed call candidate entry point, which is this verify sum function. And finally, we actually have to give it an argument, which is what is the actual sum. And this is, my answer is basically the state variable or whatever I typed into this input box. And then I'm going to await it because it's asynchronous. Get figuring out today. X, and you can see we're calling. I think it's just internet issues not letting me approve. There we go. And then we can see we have a transaction here that was created. It'll take a minute or two to pop up on the Block Explorer, and then we can see that I'm going to be the winner of the game. So that's about it. That's how you can interact with your contracts with Starknet.js. You can read and write from them, and I can throw it back to Mikey for some closing thoughts.
Thanks, Matt. Yeah. So really quickly, I'm just going to share my screen. Hopefully it wasn't too distracting with a bit of the internet latency issues, but hopefully that gave a full demonstration of how building in Cairo and using Starknet.js and everything is not that overwhelming. And we have our repo online. So if you want to learn or really learn or just have a look at what we're doing, feel free to go to the repo for Tutoring and GitHub triality.org Starknet Cairo session. And also, if you have any questions while building, we have our live site, which is triality.org. You can ask any questions there. We run community unit tests of questions. We run question and answer. So feel free to bring any questions you have to us. We're happy to help. And you can follow us on follow us on Twitter if you have any questions as well. It's basically going to help. If you have any content that you want to see, this was just kind of a game that we came up with. If you have any content that you'd like to see that could be helpful to yourself or the community, let us know, and we'd be happy to build another test repo for that. Thank you all for your time and patience, and keep on building everyone. Thanks.
Can you hear me? Okay. Hello everyone, my name is Iman. I'm a fellow at Starknet House this year. So my topic is 3D art and Starknet. So before I start, I want to claim that this is a very personal journey of my own. Since 3D art and Starknet is a huge topic, and I'm gonna speak from a non-developer perspective. I might not be able to dive too closely into the technical details. And the presentation will be more of a sharing of my experience as a designer with Starknet, combining my own background, my learnings, and my future vision. So if you're a developer, please bear with me. I'm still a beginner. If you're a non-tech background, same as me, and you're very interested in learning what possibly can be built in Starknet, then great, I will share my journey with you. So I am an architectural designer. I study architecture. So in this presentation, I'm going to share with you my projects at school and my projects in practice, and also the digital asset I've been building related to Starknet. So I studied architecture for a 3-year master's program. Basically, at school, our design sensibilities were trained through the courses called studios. So each studio from each semester has its own purpose. It has different scales, and it gets more complex throughout the semesters. For example, in this studio, I was asked to build a cider factory, and this studio is both a building studio and landscape studio. And this one is the urban complex, and we got to design our own program in a city block. As you can see, I really enjoy making models, like both physical models and digital models. This is the final section drawing for the same projects. The workflow for a studio is usually we produce physical 3D models and then move to digital models using programs like Rhino, and then we produce some 2D drawings which shows how the building is going to be built. And we want to practice. And the workflow could be quite different from what we learn at school, since we were trained to use the tools to model and to draw, we can get things done. But from my practical experience, I found two main points not very satisfying. in the current architecture industry. And one is efficiency. Big companies build their own library and like a sharing culture, not like some tech big firms, as far as I know. And some companies are still a bit protective with their own like assets, which I find not very sustainable in the long term. And second is that there we go. I don't feel I own the design, even I was part of the team. The sense of creating something was a bit lost for me. So I gradually pivot to more personal projects. I always enjoy making 3D models. I love to see how things move through the space. I love digital fabrication. I love to use tools that help me build innovative design that couldn't be done before. Can you still hear me? All right. I just want to confirm. All right, and I also explore some new modeling tools like Blender. Because they can also create some animation, like you can see here. Sometimes simply doesn't work. There we go. Yeah, just some like simple animation, like for friction, and this one is for some small projects I did for jewelry design. Yeah, those are my just explorations. And when I was building up my modeling skills, my friend introduced me to Web3, and I met Arctic in Denver and Cologne. It's a DAO meetup in last September. At that time, I knew very little about Web3, but I just kind of dived into it and want to meet people, like actual people who are doing this stuff there. And Arctic was an early community member of the game Axie Infinity. After he knew that I was an architect, he asked me to build a museum for Axie's exhibition. At that time, I was totally new to this blockchain in general, but the idea of making a virtual museum just blew my mind. I never thought I could realize the design idea in this brand new way in the virtual world. I was very happy to do this project. There are some hand drawings I did to visualize the model. I modeled in the offline program called Blender and published in the platform Decentraland. The deployment publishment of the design was actually very, very challenging for me, since I have very limited programming experience. But I learned so much from it, and most importantly, I realized how much impact the medium, the tool would have on the implementation of the design. And here are the actual museum.
Great, see you later.
So in Decentraland, each piece of land has its own coordinate system. And our slot is about 32 times 32 square meters. But we designed also some animation to the building. Yeah, just showing you how we go through the building. Yeah, the animation of the elevator that you can go to the second floor, the big exhibition room. So we placed a different piece of the art that he wants to showcase in different locations of the building, and we have some interaction with the art piece. It's hard to imagine this kind of building would exist in the meat space. Yeah, so I'm quite satisfied with the project. That you can explore different corners of the building and not following the rules in reality. Yeah, that's basically it. So moving on. So after the launch of the museum, Guilty Gilda took two of our axes that we built and put them and stored them on Starknet. So I can simply explain how he did it. So we built the model in Blender. The Blender file can be exported to GLTF format. It's a format that stores 3D model information in JSON. It's a standard format for 3D scenes and models. It's widely used in game engine and viewers. So Guilty Gills can either store the raw data, but he wants people to be able to use the model to manipulate the model. For example, to change the skin color or some textures in smart contract. So people can directly interact with it in smart contract. So in doing so, he designed a data structure using structs to host the data and store the data in smart contracts. So others can have access to it and can have access to change the model. That's how he writes it using a programming language, Cairo. And I also want to introduce you some other fantastic projects that caught my eyes when I did my research. So this one is called Meta Mandu. This is a 3D access marketplace that's pretty new. It's built on Polygon, the team. They are working towards being able to collect 3D things that work across multiple metaverse. Or they claim that it tackles the problem of creating an open metaverse. Interoperable metadata assets across engines and worlds. So for now, I feel it's still a long way from decentralization because they include 3D files in NFTs through a metadata structure, and the model data are not stored on chain. So compared to Polygon, Starknet is more long-term and promising. I envision in the near future, the idea will be realized on Starknet with more on-chain solution. Yeah, I have more projects that I want to store on-chain. I imagine other designers or gamers can grab them, create characters or storylines based on my characters. Starknet is a very suitable place for procedural design as well. For example, any kind of like procedural generation design. For 3D generated art, it will have more application. So yeah, that's pretty much all of my presentation. Yeah, thank you so much. Thank you so much for your attention. It's a pity I couldn't be there, but I'm really happy to present on my work, and I will keep doing my research, yeah, and keep showing my research with you guys. Thank you so much.
저는 스타크넷 하우스의 리서치 펠로우로 참가하게 된 한기욱이라고 합니다. 제가 오늘 말씀드릴 이야기는 스타크넷의 모바일 생태계에 관한 이야기를 들려드립니다. 2018년도 당시에 블록체인이 큰 이슈였을 거예요. 저도 마찬가지로 블록체인에 관심을 있었습니다. 그래서 블록체인 컨퍼런스도 많이 돌아다니고 이런저런 활동을 했었는데 그때 당시에 제가 블록체인 전반기에 두 가지가 있었습니다. 첫 번째는 확장성 이슈가 있다고 생각했고요. 그리고 두 번째는 많은 사람들이 관심을 블록체인에 쏟고 있지만 그 쏟고 있는 관심이 주로 그저 투자에 그 이상으로는 가지 못한다. 그 이상에는 딱히 관심이 없다는 생각을 그때 가지고 있었고요. 그래서 이런 문제들 때문에 아직 뭐 실질적으로 어떤 프로덕트를 만들고 싶지 않다. 이 블록체인 네트워크라고 생각을 해서 관심도가 많이 떨어졌었습니다. 그래서 그 이후에는 이제 AI라던가 빅데이터라던가 그런 쪽으로 관심을 두게 됐고, 그래서 이제 제가 그래프 데이터베이스를 이용해서 널리지 그래프를 만든다든지 이런 쪽 일을 하고 있던 와중에 이제 스타크넷 하우스라는 프로그램을 알게 돼서 스타크넷 하우스에 어플라이 했고, 그래서 이렇게 다행히도 붙어서 이렇게 참가하게 됐습니다. 스타크넷 하우스에 어플라이 했던 가장 큰 이유는 이제 올해 초에 제가 블록체인 필드를 다시 들여다봤는데요. 물론 그 전에 굵직굵직한 NFT나 디파이 같은 경우들은 저도 알고 있었지만 블록체인 필드에 다시 관심을 가지고 들여다보게 된 것은 올해 초가 맞지 않나 싶습니다. 그래서 들여다봤는데 제가 2018년도 당시에 느꼈던 가장 큰 문제라고 생각했던 첫 번째 문제, 그 확장성 문제에 해결책들이 많이 제시되고 있다는 걸 느꼈고, 특히 이제 지케롤 같은 경우는 디센트럴라이즈 앱을 만들기에 최적의 조건일 수 있겠다라고 생각을 해서 관심을 더 가지게 됐습니다. 그래서 스타크넷 하우스, 근데 사실 이제 회사를 다니고 있는데 회사에서 하는 일은 그래프 데이터베이스를 이용하는 일이었기 때문에 딥다이브를 했다고 보긴 힘들었는데요. 스타크넷 하우스에 들어가서 이제 거기 이제 같이 있는 리서치 펠로우들과 그 앞선 그 프레젠테이션을 맡았던 이란도 같은 하우스에서 함께 지냈었는데요. 인하우스에서 다른 이제 펠로우들과 리서치 펠로우들과 인하우스 멘토와 이런저런 관심사를 공유하다가 제가 생각했던 두 번째 문제에 대해서도 의견을 나눌 기회가 있었습니다. 근데 제가 생각했던 두 번째 문제, 그 사람들의 관심이 그러니까 디센트럴라이즈 앱이나 웹3에 있는 게 아니라 그냥 투자에만 더 관심이 있는 것 같은 거에 대해서 이야기를 나눴는데 다른 이제 펠로우도 나도 어떤 이제 웹3에 도움이 되는 어떤 프로토콜을 만들고 싶은데, 근데 이게 사람들이 다 코인 이렇게 사고 팔고에 관심이 있고 디파이에 관심이 있고 NFT에 관심이 있는데 내가 만드는 프로토콜이 지금 나는 필요하다고 느끼지만 지금 실제로 시장에 나오면 쓰일까? 라는 이야기를 많이 하더라고요. 그러면서 그 친구는 이제 그래서 내가 이 프로토콜을 만드는 것보다 다음 슈퍼스타 NFT나 디파이 같은 다음 블록체인의 슈퍼스타가 나오는 것을 기다리거나 내가 다음 슈퍼스타를 만들거나를 해야겠다라고 이야기를 했습니다. 그러니까 이제 이용자층을 넓히고 이용자들의 관심 분야를 보다 더 넓히고 싶다, 이런 이야기를 했던 건데요. 저도 그 말에 동의를 하고, 하지만 저는 다음 슈퍼스타를 만들고 다음 슈퍼스타를 기다리기보다 스타크넷이 이미 디센트럴라이즈 앱을 만들기에 좋은 환경을 구축해놨다고 저는 생각하기 때문에 이 스타크넷을 이용해서 웹3에 관심이 없는 다른 사람들의 인터레스트를 어떻게 웹3 쪽으로 끌고 올 수 있을까라는 생각을 많이 했습니다. 근데 제가 생각하기에는 사람들의 관심, 많은 대중의 관심을 끌기 위해서는 모바일 생태계 쪽으로 접근하는 게 보다 더 접근성이 뛰어나겠다라는 생각을 했습니다. 그래서 많은 사람들이 핸드폰은 다 갖고 다니고 핸드폰을 컴퓨터보다 더 많이 사용하는 사람들도 있을 테니까요. 많으니까요. 그래서 모바일 생태계에 대한 관심이 생겼고 이제 모바일 생태계에 관심이 생겨서 그렇다면 내가 모바일 생태계에 기여를 해서 보다 많은 사람들이 웹3에 관심을 갖게 해야겠다라고 생각을 했는데 스타크넷에는 모바일 월렛이 없었습니다. 그러니까 며칠 전에 브라보스가 모바일 월렛을 런칭하긴 했습니다만 그 전까지는 없었고 그리고 브라보스의 모바일 월렛도 제가 지금 알기로는 모바일 네이티브 앱은 지원하지 않고 웹 브라우저를 추가해서 웹 브라우저 인앱에 앱 안에 웹 브라우저가 있어서 지금 있는 아스펙트 같은 웹 기반의 앱을 지원하는데 저는 특히 모바일 네이티브 애플리케이션 쪽을 지원하는 모바일 월렛이 필요하다고 생각해서 저는 이번 스타크넷 하우스 프로그램의 목표로 월렛을 만드는 걸 목표로 생각했고 그리고 아마 그 이후에는 또 다른 모바일 애플리케이션, 그러니까 모바일 월렛을 만든 다음에는 또 다른 모바일 애플리케이션을 만드는 데 주력을 할 것 같습니다. 이게 기본적으로 제 이번 스타크넷 하우스에서 스타크넷 펠로우들과 멘토들과 함께 진행하는 제 개인 프로젝트에 대한 간략한 소개였습니다. 이상입니다. 감사합니다.